and in this course, I'll be guiding you through the ins and outs of the TypeScript programming language. TypeScript is designed to be compiled into fully compatible JavaScript. In this course, I'll show you everything you need to know in order to create full-fledged JavaScript applications using the TypeScript programming language, starting by revisiting some JavaScript fundamentals and proceeding all the way to demonstrating how to convert an entire existing JavaScript codebase to take full advantage of what TypeScript has to offer. TypeScript's tooling is fully cross-platform, which means that you can develop TypeScript applications using Windows, Mac, or even Linux. Microsoft even offers an online editor in order to get your feet wet without having to install anything at all. JavaScript is an amazing language. It's been around for over several decades, and it's everywhere, from your browser to the server. It even runs some refrigerators. JavaScript is also a dynamic language, which means that it is very forgiving in how it allows you to define and use variables. For example, you may decide to create a variable and assign it to a string value, then reassign that same variable to a complex type that you define on the spot, and then go ahead and add properties to that object. JavaScript allows it all. In fact, that's the beauty of the language. But JavaScript's dynamic and forgiving nature is both a great thing, allowing you to do virtually anything you want, and a bad thing, allowing you to make all the mistakes you want as well. For example, take a look at this piece of code. There are at least 3 errors in just these 3 lines of code. All of them will break my application at runtime, and only really one of them is obvious enough to find just by looking at this code. In other words, my app is broken, and I'm not going to find out about it until it's running. At this point, you might be a little confused, perhaps thinking that maybe the wrong course started playing. If this is a course about TypeScript, why am I talking about JavaScript? Well, I'm talking about JavaScript because TypeScript is designed to catch exactly these kinds of problems in your JavaScript code. TypeScript adds strong static typing on top of JavaScript, which means that it's able to provide compile time code checking that will not only catch many common issues before you even run your code, but will also help you write your code by providing first-class, inline documentation and guidance. But perhaps the most important thing is that TypeScript is a superset of JavaScript, which means that it extends the JavaScript language with all of this additional goodness rather than creating a whole new language. Plus, once all is said and done, TypeScript code compiles down to JavaScript. So anywhere that you would use JavaScript, you can use TypeScript, after you compile it at least. In other words, TypeScript is JavaScript. So if you already know JavaScript, then you're already well on your way to knowing TypeScript. So just keep watching, and I'll show you everything you need to know in order to take advantage of this powerful language. TypeScript is a superset of the JavaScript language, which means that you'll need to compile your TypeScript code into JavaScript in order to run it in a browser or other JavaScript-based environment such as Node. So before we get into the TypeScript syntax, we first need to install the TypeScript compiler. To begin, head on over to typescriptlang.org/download. Here you'll find a number of ways to bring the TypeScript compiler into your project, depending on what tools you may be using. In this course, however, I'm going to be relying on the NPM environment, since that's what I expect the majority of JavaScript applications are using these days. Or if your project isn't currently using NPM, it's easy enough to add it without disturbing anything else. Note that the TypeScript downloads page actually shows 2 ways to install TypeScript: in your project or at the global level. This means that it's available for your entire machine. I'll get back to this in a minute. But first, regardless of where or how you install TypeScript, if you don't already have Node, you'll have to install it by heading on over to nodejs.org and follow the instructions for installing Node and NPM for your particular environment. you'll probably have the best luck with whatever the current LTS version is. I've already got Node and NPM installed, so I'm going to skip this step. Once you've made sure Node and NPM are installed, it's time to install the TypeScript package. I highly recommend that you install TypeScript at the project level so that each one of your projects may use a different version of TypeScript and you can manage them independently without worrying about one project breaking another. To do that, simply copy this line, head on back to your project, open a terminal in your project's root folder, and paste and run this command. This command tells NPM to install the TypeScript package into your local project as a dev dependency, meaning that it'll only be needed at development time and not used by your application at runtime. At this point, if I were adding TypeScript to my project, as I usually do, I'd simply hit enter here. However, since I'm going to be jumping around between projects and folders throughout this course, I'm actually going to install TypeScript to my entire machine using the global method I mentioned earlier. To do that, I'll simply remove the save dev part of this command and replace with -g to indicate that it should be installed at the global level. Now I'll hit enter and install the TypeScript compiler globally. Note that, like this user, your user may not have the privileges required to install at the global level. Since I'm on a Mac, I'll just rerun this command with the sudo application to gain temporary privileges like this. You'd use this same command if you're on a Linux machine too. If you're using Windows, you'll need to execute this command in an admin console. After the command completes, I can ensure everything was installed correctly by running the TypeScript compiler executable TSC using the -v flag to display the version. This command worked without any errors, which means I'm ready to go. Now, don't worry if your version of the TypeScript compiler is higher than mine, even if it's a lot higher. Generally speaking, new versions of TypeScript are pretty backwards compatible, so even if your version is higher than the one you see here, everything I show in this course will still work for you. In the introduction to this course, I showed you TypeScript in action, adding valuable static typing to your projects. In order to gain access to this information, however, you'll need to configure TypeScript in your application. If you're using an editor that has built-in support for TypeScript, such as Visual Studio Code, like I'm using here, the only thing you'll need to add is the TypeScript configuration file to the root of your application's codebase. This file is called tsconfig.json. There are plenty of configuration options available, but I'm going to start with just one. Include. And I'll supply it a parameter of the paths to the files that I'd like to include. Here I'm telling it to look for all of the files under the src or source folder under this current folder. This defines the scope of this TypeScript project. Now I can save this file and run the TypeScript compiler to see what happens. And I see the output, no inputs were found in config file, which means that the compiler didn't find any files to compile. So let's create one now. First, I'll create that src or source folder that I mentioned earlier. And then I'll create a new TypeScript file, which is just a file with the .ts extension. Then I'll add some JavaScript to it. Now if I run that tsc command again, I'll see there's no output, which actually means that everything ran just fine. How do I know? Well, if I look in the src folder, I now see two files, the demo.ts file that I created and the new demo.js file. That's the output of TypeScript's compilation process. If I open up this new file, I can see that TypeScript has taken my code and transpiled it down into JavaScript that is more compatible with a wider variety of browsers and runtimes. In fact, you're able to control which JavaScript version TypeScript targets in the tsconfig file. You can find almost all of the TypeScript settings in the compiler options section. The option I'm most interested in right now is the target option. As you can see here, this option defaults to ES3, which stands for ECMAScript version 3. As of the time of this recording, the majority of browsers in use today support ECMAScript 6 or ES6, so that's usually a great choice. Now, when I run the tsc command again, and I inspect the output, I can see the JavaScript that TypeScript has emitted has changed. Since ES6 supports the class keyword natively, TypeScript knows that there is no conversion to be done and simply writes the class out as is. It can also tell that the 3 properties I defined on the class were never used, so it knows that it's safe to strip them out from the final output. TypeScript's default behavior is to render JavaScript files right next to TypeScript files. However, if TypeScript is the only tool you'll be using, you'll probably want to direct the output to another folder. To do this, simply set the outdir setting to the folder where you want the generated files. Then delete the generated demo.js and run the tsc command again. Once it's finished, I can see the file has now been created in the new build folder. If, however, you plan on using TypeScript only for its type checking ability and will rely on another tool, such as the Babel compiler, to transpile the final output, then an even better value for the target setting is ESNext. This setting tells TypeScript to emit code that is compatible with whatever the latest version of JavaScript happens to be, which effectively just means that it should strip out all of the type annotations and pass the rest of the code onto the other tools. And finally, if you do plan on using TypeScript only for type checking and nothing more, it's also a good idea to set the no emit setting to true, which tells TypeScript not to write out anything to disk at all. If I do this and then delete the generated folder, then run the tsc command again, I see that my type checking is working perfectly fine, but no files are being generated anymore. Now that I have a basic TypeScript configuration in my project, it's time to move on and see what else it can do. At this point, I've now shown you how to add TypeScript to your application and compile TypeScript files. However, one of my favorite things about TypeScript is that it is very easy to add to an existing application with existing JavaScript code. This is because TypeScript is a superset of JavaScript, which means that all JavaScript is valid TypeScript. If you open the exercise folder for this video, you'll see that I've added an example JavaScript file, app.js. To enable checking of existing JavaScript files, I'll simply add 2 additional settings to my tsconfig.json file. Allow.js and check.js. And I'll set both of these options to true. Now I'll run the TypeScript compiler and see what happens. TypeScript found 3 errors in this new JavaScript file. Errors that I planted in order to show how TypeScript can help you, even with JavaScript. I'm actually going to skip this first error, cannot find $, because it means that TypeScript doesn't know anything about the jQuery library I'm using, and I'll show you how to fix that in the next video. The next 2 errors, though, show how TypeScript is able to look at my JavaScript code and see that I'm trying to reassign 2 properties to values that are a different type than they were previously assigned to. To see how it came to this conclusion, let's follow the code. It starts on line 14, where I call the getContact method, which is defined on line 1. And TypeScript can tell that this method returns an object with 3 properties: ID, name, and birth date. And even more, it can tell that the ID property is a number and the birth date property is a date value. So when I go to reassign those properties to other types on lines 15 and 16, TypeScript lets me know that this is probably a mistake. Now, when I change them to the correct types, and run the compiler again, those errors go away. Now that I've fixed some of the errors that were obvious to TypeScript just based on its ability to infer type information, let's add some more information to allow it to detect even more issues. And no, I don't mean converting this file to TypeScript by renaming it to .ts. I mean adding types to the JavaScript code using the industry standard JSDocs syntax. The basic JSDocs syntax looks like this. True to its name, it's just a comment block, but with some special syntax identified by the @ symbol. In this case, Visual Studio Code's autocomplete has actually looked at my code and determined that this function that I'm documenting has a parameter named contact ID and has defined its type, in the braces, as star, meaning it could be anything. However, if I change the star to number, which is what type I expect this parameter to be, I can now hover over the parameter and see that TypeScript has determined that this is indeed a number value. What's more, if we look down on line 24, I can also see that TypeScript has found another error in my code. I'm trying to locate a contact using a string value rather than a number value for the contact ID. Well, that's not correct, so I'll fix it. And I'll see that the error goes away. And that's just one of the dozen or so JSDoc keywords that you can use to tell TypeScript about your JavaScript code without actually converting your JavaScript files to TypeScript. In fact, you can mark up just about all of your JavaScript code like this. However, if you're going to go that route, I would just recommend taking the time to fully switch to TypeScript instead. In the previous video, I showed you how to use TypeScript to parse JavaScript files without actually converting them to full-fledged TypeScript files. I also showed you how TypeScript found a few errors, and I fixed most of those errors, but I left one. The one in which TypeScript warns me that it doesn't know what the $sign means, or rather, it's not aware of the jQuery library that I'm using here. Since TypeScript has been around for quite some time now, you'll probably find the majority of the JavaScript libraries you use will already have TypeScript support built in, especially if you're installing them from the npm package repository. However, it is likely that at some point you will run across a library that doesn't offer TypeScript support, particularly if you are migrating an older application or one with a lot of custom code. In these cases, you've got two options. You can create the type definitions yourself, or in the case of an open source library, you can install type definitions that others have created online, hosted in the definitely typed repository, which you can find at github.com/definitelytyped/definitelytyped. Here, under the types folder, you'll find the type definitions for literally thousands of open source libraries. In fact, this list is so big, GitHub doesn't even show the whole thing at once. But don't worry, you don't have to search here because all of these folders are published as packages in the npm package repository, npmjs.com. And this site is much easier to search. Simply search for @types and see what you find. In my case, I'm looking for jQuery, so I'll search for the @types jQuery package. Once I find what I'm looking for, I'll simply copy the command from the site and execute it in the root folder of my project. Once this is done, you'll see that this command has downloaded the package from the npm repository and extracted it to the node modules folder. And inside of that folder, there will be a types folder with a jQuery folder inside of that. This folder contains all of the jQuery TypeScript definitions. The most important files will be the ones with the .d.ts extension, TypeScript declaration files. If I open the one named jQuery.d.ts, I'll see a bunch of relatively advanced TypeScript code, mixed with some pretty impressive documentation. More importantly, if I switch back to my JavaScript file, where TypeScript was previously complaining about the missing jQuery definitions, I can now see that not only is TypeScript no longer complaining, but I actually have really good autocomplete and inline documentation to help me use the library. And that's how you import open source type definitions. Now, what about your own internal JavaScript libraries? Well, you'll be using the same .d.ts files. You'll just need to manually add them to your project yourself. I'm not going to lie, writing these definitions from scratch can be quite daunting. Heck, it could be an entirely separate course. However, you could probably get a long way by simply taking a look at some of these publicly available definitions and copying from them and modifying them yourself. It'll be a lot of work, but if you have JavaScript libraries that you use in a lot of different projects, it might just be worth it. In this chapter, I showed you how to add TypeScript to an existing application and convert your existing JavaScript files to TypeScript. Your challenge is to take this JavaScript application here in the exercise files and convert it to TypeScript just like I did. Be sure to write the new JavaScript files to a different folder. You'll know you're done when you're able to run the TypeScript compiler and it outputs JavaScript files in your target folder. This should take you around 5 minutes to complete. In this challenge, I had you convert an existing JavaScript application to TypeScript and have the compiled JavaScript output generated into a new folder. In order to accomplish this, you had to do the following. First, install the TypeScript compiler if you hadn't already. Then create a new file named tsconfig.json in the root of your project folder. In this new config file, you had to define the input file paths, then add a new configuration section, define the version of JavaScript that you wanted to target, define the output folder path to the folder that you wanted to output your JavaScript files to, and finally rename the JavaScript files to the .ts extension. With this in place, you can see if you're done by jumping out to the terminal and executing the tsc compiler command to produce the compiled JavaScript output. If your output folder looks like this one, then congratulations, you've successfully converted the JavaScript application to TypeScript. If you had any problems, however, feel free to rewatch this video and the corresponding videos in this chapter to fill in any gaps. In the previous chapter, I showed you how to add TypeScript to your application. I also showed you how to configure TypeScript to inspect your JavaScript files and provide some pretty impressive type checking simply by inferring or implying type information from your existing code using nothing but basic JavaScript syntax. In this chapter, I'll show you how to not only explicitly provide TypeScript with type information, but also move beyond those simple built-in types and create your own custom types. Before I show you how to build custom types, however, let's start by showing the basic TypeScript syntax. I'll start with regular old JavaScript. Here, I'm creating a variable named x and assigning it the numeric value 5. And just like I showed in the last chapter, if I hover over x, I can see that TypeScript has inferred that because I initialize the variable with a numeric value, the type of this variable is number. This is called type inference, and it's one of TypeScript's most powerful and impressive features. However, if I remove the assignment, TypeScript no longer has enough information to infer the type. So in this case, or in any case that I need to explicitly define a variable's type, I can do it with this syntax. A colon followed by the name of the type, in this case, number. I can use this syntax to define any types that I want, like this. I can even identify array types. And if I try to assign one of these variables to a value of the wrong type, TypeScript shows me errors. So that's the basic syntax that lets me give TypeScript the information it needs to help keep me from making mistakes. But let's back up a minute. What happens when it's not a mistake? What happens when I actually want to assign a different type to an existing variable? That kind of dynamic behavior is, after all, part of the power of JavaScript, right? Enter the any type. By defining this variable as the any type, I've told TypeScript that this variable can literally hold any value of any type. In addition to defining a variable as the any type, I can also use TypeScript type casting to tell it to treat any value as the type any. For example, rather than defining the variable b as type any, I could cast the string value I wanted to assign to the any type instead. For example, rather than defining the variable b as type any, I could cast the string value I wanted to assign to the any type instead. And now we can see that the error goes away. Now, using any can seem like a useful way to reduce the many type checking errors you may see when you first start introducing TypeScript to your projects. And there may be many times that you may feel you have no other way to get rid of those pesky errors other than using the any type like this. However, the any type has a significant downside. By using the any type, you're effectively telling TypeScript, don't bother including this type in type checking. Trust me, I've got it handled. However, this goes against the entire point of using TypeScript in the first place. Although this is a perfectly legitimate syntax, and the any type is a perfectly legitimate type, you can think of the rest of this course as providing you with the tools you'll need in order to express the exact types you want and allow you to avoid ever having to use the any type in your projects. Now that I've shown you the syntax to tell TypeScript about primitive and built-in types, it's time to define our own custom type using what TypeScript calls an interface. The syntax to define an interface is pretty straightforward. Just the keyword interface, followed by the name of the interface. I'll call this one contact, followed by open and close braces, Then inside these braces, we can begin adding the properties that we want this interface to have. For example, let's say a contact should have an ID field with a type of number, a name with a type of string, and a birth date field with a type of date. Now, if you're familiar with the more recent versions of JavaScript and the class syntax, this might look incredibly familiar. In fact, any class definitions created using the JavaScript syntax can also be used as interfaces. The biggest difference between an interface and a class, however, is that interfaces strictly exist as a way for you to provide type information to TypeScript. They are only ever used at compile time and are never available and will never even appear in your runtime code. Now, once you've defined an interface, it can be used just like any other built-in type, like this. Here I've created a variable named primary contact with the type of our new interface, contact. But things don't get very exciting until we try to assign a value to this variable. For example, I'll start by just creating an empty JavaScript object and see what happens. Because I've defined this variable as a contact type, and TypeScript knows the fields that a contact type has to have, TypeScript is able to provide me with much better auto-suggest capability, showing me the fields that I can add to this type. What's more, TypeScript is complaining that the value I'm trying to assign is not a valid variable because it's currently missing all of those fields. So let me go ahead and add them. Now that I've provided fields with values that match the types described by the interface, all my errors go away. And it should come as no surprise that if I set one of these fields to a value of the wrong type, TypeScript warns me of my mistake. What if you define an interface with many fields, but don't always expect every field to be populated? For example, in the case of the contact interface, what if we don't always need to have the contact's date of birth? Luckily, TypeScript allows us to define any one of an interface's fields as optional by appending a question mark to the field's name in the interface definition, like this. Notice that once I make the birth date field optional, my compilation error immediately goes away. What this does is effectively tell TypeScript that, in this case, not every contact will always have a birth date field, so don't require this field in order to consider something a valid contact. However, the interface does still enforce typing on this field when it does exist. In other words, not every contact must have a birth date field, but when a contact does have this field, it must be a date. So even though I don't currently have any errors in this code, if I try to re-add the birth date field, but assign it to a string value, TypeScript does not allow it. However, if I go back to using the proper date type, TypeScript is happy once again. As if that weren't powerful enough, multiple interfaces can be combined to create brand new ones. For example, let's say that I want my contact interface to also include the contact's address. I could do that by adding those fields to the contact like this. Now, this would work fine until I wanted to use those address fields somewhere else. So instead, I will move them to their own interface called address. And then I can merge them back into the contact type using the extends keyword. Doing this merges the address interface into the contact interface to create one big interface. With this code in place, I can now assign those address fields to my contact objects. With this code in place, I can now assign those address fields to my contact objects while still being able to reuse the address type anywhere else in the application that I need to. Interfaces are a fundamental building block of creating a fully typed application with TypeScript. And I hope these examples show how simple and how powerful interfaces are, as you'll be seeing quite a lot of them throughout this course. So far in this chapter, I showed you how to use the primitive and built-in types that JavaScript offers, as well as how to define your own custom types using interfaces. One other way of referring to types and defining your own custom types is called a type alias. As its name implies, a type alias is simply providing an alias, or alternate name, for an already existing type. You define a type alias using the type keyword, followed by the name of the alias. Let's call this one contact name. Then follow that with an equals sign and the type that you wish to alias, in this case, string. Now that I've defined the type alias, I can use it in any place that I would use the original type. For example, I can refactor the contact interface example from the previous video, changing the type of the name field from string to contact name. Note, however, the type aliases are truly just that, an alias for another type. They are not a new type themselves, which means that they can be used interchangeably with the type that they alias. For example, even though I've now defined the name field of the contact interface as the type contact name, I can still assign it to a regular old string value. So what is the value of type aliases, you may be wondering? Well, even when used to give another name to a primitive type, as in this example, I think they add a little more meaning to the field or variable that they're describing. For instance, in this case, it's not just a string value, but a contact name value. And if I wanted to change all references of contact names, I could simply change the type that the contact name alias refers to. If that justification doesn't satisfy you, however, I don't blame you. But hold out judgment for just a little while, because later in this course, I will show you some more advanced uses of type aliases that will probably have you changing your mind. When you write code, you'll often need to reference various kinds of hard-coded values. For instance, let's say that in our application, a contact can also have a status value, which indicates the various states that a contact can be in, such as active, inactive, new, or otherwise. In order to add this property, I could define it as a string property like this, which would allow me to assign the values I need, like this. Like active or inactive. The problem with this approach is that the string type allows me to assign any string, such as, or consider a more nefarious example. This one is a misspelling with a 1 instead of an I that would introduce a variety of bugs that would be very difficult to spot. Now, our fictitious company and our application may be concerned about happy customers, and maybe we hope that as developers we never make typos, but I don't ever want to allow either of those two values to be assigned to this field. And TypeScript can help me with that in a few ways. The first technique that TypeScript offers to avoid mistakes like these is called an enum. Enums are a special type that has a hard-coded list of values and is defined like this. Once an enum is defined, I can refer to it just as I would any other type. In our contact case, I can replace my string type with the contact status enum. Unlike many other TypeScript syntaxes that get stripped away at compile time, enums do get compiled along with the rest of your code. This allows you to refer to these types at runtime like this. This is not a drop-in replacement for string values, however. If I hover over the value, I see that TypeScript tells me that this enum represents the value 0, since it's the first value that I defined in the enum. TypeScript does, however, allow you to use string values in your enums. It's as simple as this. Here I've used the same words in lowercase. However, you can use whatever string or number values you like, as long as every value in the enum is the same type. With this change in place, I can now hover over the value again and see that the value at runtime will be the string value active. This value and all other enum values you define will be the same everywhere you use them. More importantly, because TypeScript knows all of the possible values, it can give you much better autocomplete suggestions and even output compilation errors if you manage to use an enum property that doesn't exist or is spelled wrong. In a previous video, I showed you how to apply type information to variables. But seeing as how functions are a very important part of JavaScript development, it's nice to know that this same syntax can be applied to them as well. For example, this is a JavaScript function that accepts an object and returns a clone of that object. If we wanted to restrict this method to only allow contact types as input parameters, we could simply apply a type to the parameter like this. Now for the return type. Since TypeScript is incredibly intelligent about reading your code and inferring types, for many functions, you can usually get away with not supplying a return type at all. For example, if this method were simply to return the parameter it was given, I can see that TypeScript has correctly determined the return type will be contact. Likewise, if I were to return a string value, TypeScript says the return type is string. But let's go back to the original code. Now, it's obvious to us as JavaScript developers that the return type of this function should match the type of the parameter passed into it. In other words, given this code, it seems clear that if the type of variable A is contact and the variable B is a copy of variable A, then the type of variable B should also be contact. However, that's not the case. Since the object.apply function used in this clone function returns the any type, that's what TypeScript infers the return type of this whole function to be. And since we're assigning that value to variable B, that's the type that TypeScript infers variable B to be as well. To fix this, we can apply the same type syntax to state the return value of the function that we apply to variables. Now, everything is correct. In JavaScript, functions can also be passed as variables. For example, we can rewrite this clone function to accept a function as a parameter rather than an object. We can, of course, provide type information for function variables as well. It looks like this. This resembles a function's signature. It starts with a list of parameters contained within a pair of parentheses, in this case a single parameter named source with the type of contact, followed by equals, greater than, and then the return value, contact. Finally, there is one last function syntax, and that is the way that you would define a method on an interface. It looks like this. This syntax is similar to what we just saw, but with a colon instead of the arrow syntax we just used. Likewise, if this method were to accept any parameters, they would be defined like before. Now our functions are fully typed. In the previous video, I showed you how to apply TypeScript typings to a function's parameter and return values. In this video, I'm going to show you how to take that syntax one step further with what might be considered TypeScript's most powerful feature, generics. A generic type is simply a metatype, a type that represents any other type that you might want to substitute in. It's easiest to understand a generic type and the power it brings by simply showing it in action. And that clone function from the previous video is a great candidate for generics. Let's take a look and see why. In the previous video, in order to give TypeScript enough information to be useful, I had to supply a specific input type and return type. In this case, the method accepts a contact parameter and returns a contact value. But if we take a look at the actual code in this function, there's nothing specific to a contact at all. In fact, this function can take almost any object and return a clone of that same type. Enter generics, which allow us to replace both of those references to the contact type with a placeholder type, something that can be substituted for a different type each time the method is used. To convert this to a generic function, I start by defining the generic type parameter right before the parameter list, like this. Here I've used the generic type name t, but this is just a convention that most people use. You can use any valid type name. Then, once I've defined the generic type, I can begin using it to replace any other type in the function's definition, like this. I've now told TypeScript to use the same type for the input parameter as well as the return value. In other words, whatever type is passed in will get passed right back out. For example, if I hover over the return value of the existing call that I made to the clone method, I can see that TypeScript continues to correctly determine that a clone of variable a, which is a contact type, should also be a contact. But let's try another example just to really see how powerful this actually is. Here I've declared a variable without explicitly defining a type, and then I've passed that variable through my generic clone method. In this example, TypeScript dynamically replaced the generic placeholder type t with the structure of this variable that I've passed in, and that type flows all the way through to the variable that I assign the return value to. Now, you don't have to stop at one generic type parameter either. You can define as many as you wish. For example, here I've defined two generic type parameters that can each be used to refer to different types. When I use generics in this way, however, a way in which TypeScript cannot easily infer what they should be, I have to set them explicitly when I call the method using this syntax. Here I've used the contact type for both parameters, but I could have just as easily done something like this. One final feature of this syntax is something called generic constraints, which allow you to place more restrictive rules around the types that may be used as generic type parameters in your functions. For example, if for some reason I wanted to allow this clone method to accept multiple generic type parameters, but I wanted to make sure that the return type matched the input type, I could restrict the types that may be used for the second t2 parameter using the extends keyword like this. This would allow me to supply any type I wanted as the second generic type parameter, but it would have to at least match the properties of the first type parameter. For example, if I add another type that matches the signature of my contact type, I can use that as the second type parameter. Note that the extends keyword doesn't mean that the second type literally has to extend or derive from a given type. It only has to match it and then add any other properties that it likes. In this example, I've created an entirely new interface, user contact, that has no direct relationship with the contact type. It just happens to share the same properties that the contact type defines, and that allows it to satisfy the extends constraint. One last thing about generics, they're not limited to functions. They can be applied to interfaces and classes too. Take this example. Here I've used the generic syntax to define a generic type named tExternalID on the user contact interface. Once I've defined the generic type, I can then refer to it whenever I want inside of the interface, whether it be the type of a property or even the generic parameter to another interface. As you might be able to tell, generics are an incredibly powerful tool in your TypeScript toolbelt, one that you'll be using quite a bit. And guess what? This video only scratches the surface of what you can use generics for. Keep your eyes peeled because you'll be seeing a lot more of them and a lot more advanced usage of them throughout this course. In this chapter, I introduced you to a number of ways to apply types to your JavaScript code. For this challenge, I've given you a JavaScript application in your exercise files. I've already created the tsconfig.json file, but your challenge is to find a place to apply each of the techniques that I've shown you in this chapter. First, create an interface to describe the structure of this variable. Hint, it's an array, so you want to define the interface for the type of items that are in the array, not the whole array. Next, I want you to strongly type some hard-coded values with an enum. Then apply types to the parameters and return values of these functions. And also use a generic parameter to define the parameter type of this function. This one will probably take you a little bit longer to finish. You might be able to finish it in under 15 minutes, but don't be disappointed if it takes you longer than that. In this challenge, I showed you a JavaScript application that had just been converted to TypeScript, but lacked any kind of additional type information, and I asked you to give it that type information. Here's how I solved this challenge. First, I asked you to create an interface to describe the structure of this variable on lines 1 through 5. The way I would approach this is, first, come up with a name. What are we looking at here? It's an array of to-do items, so I'm going to call my interface something like to-do item or just to-do. Next, I'm going to take a look at what is similar and what is different in these items. They all have an ID, that's a number, a title, that's a string, and a status, that's also a string. Also, one of them has a completed on property, which is a date value. However, this is not always present on all to-do items, so I'll make this one optional. Then, once I have my type, I can apply it to my variable. Next, I challenged you to strongly type the to-do status values using an enum to make sure they're consistent everywhere. First, I'll create a new enum type named to-do status. Then I look at the different statuses that are being used. It looks like there are 3: to do, in progress, and done. So I add them to my enum. But if I do it this way, I'll break the in-progress value since the original value has a hyphen in it, but my new enum value does not. So I'll give it a value. In fact, I'll give all of my enums better looking names and explicit values. Now that I have my fancy new enum, I can use it as the type of my status property. And then I'll update all of my existing references. Next, I challenged you to apply types to the parameters and return values of the two functions in this code. This part is simple. Since we've already created the to-do interface, we can use basic type syntax for the parameters and the return type. From looking at the implementation, I can see that this function accepts a string parameter and returns the newly added to-do item. Finally, I challenged you to apply generic types to the getNextID function. I'll start simply by defining a generic type T for the items parameter. But since this function expects an array of items, the parameter type will actually be an array of T. And the function always returns a numeric value no matter what T may be. Now that I've done this, I can see these new errors are telling me that a simple generic parameter like this one won't be enough. I have to tell TypeScript about the ID property that I'm using in this type. So I'll add a generic constraint that says that any one of these parameters must be an object with a property called ID of type number. And that's it. We have fully typed this application. Now, there's no one single way to do any of this. So your solution may have varied a decent amount from what I have here. But as long as you were able to get all of these typings in place, then your solution is just fine. Also, I've included my solution in the exercise files, so if you have any problems or just want to see my completed code, feel free to check it out. In a previous video, I showed you how to use the type keyword to define simple type aliases or pointers to another type, like the one on line 1 here. Type aliases referring to a single value like this are helpful. However, defining type aliases that combine multiple types together to create new, more dynamic and powerful types is far more useful. For example, let's revisit the contact type that I've been building throughout this course. Here on line 11, I've used a simple type alias called contact name to give a better name to a string type. However, this interface also includes an even better example in the birth date field. Right now, this field is defined as the JavaScript date type. However, this field is a great example of how many applications take advantage of JavaScript's dynamic nature to allow fields like this to hold both a date value and a number value, which is the output of the date.now function. Or perhaps some applications may even want to accept a string value in this field as well. As it's defined now, this contact interface would not accept anything but a date value. However, I can update this field to accept any of those three types using the pipe syntax like this. This syntax allows you to provide a list of as many types as you want to support in a field. What's more, TypeScript is intelligent enough to apply this information to the logic in your code. For example, take a look at this function that might operate on this field. This function uses standard JavaScript operators to inspect the type of the values at runtime to determine how to treat them. The first two conditions contain logic to handle number and string values. And since we've already told TypeScript that this value can only be one of three types, and we've already handled two of those types, then TypeScript is smart enough to derive that this last case must be the date type. Now that we've seen how powerful this approach can be, let's take this type that's been defined inline and use a type alias to give it a name. I'll simply copy it, use the type keyword to create an alias, and then paste the inline type. I'll replace the existing definition with our new type alias. Another use of the type alias syntax is to combine multiple types together to create an entirely new type. For example, I'll revisit the interfaces video where I use the extends keyword to extend the contact interface from the address interface to bring in all of the fields from the address interface into a contact. But what if we want to have two different types of contacts, one with address properties and one without? Well, I could use the extends keyword to create a new interface for that. Or, since this is a situation where I'm not actually defining any additional fields, I could use another type alias syntax to accomplish the same thing. Unlike the pipe syntax, which provides alternative types, using the ampersand syntax like this combines the two types together to create an entirely new type. One last usage for type aliases also happens to be my favorite, and one that I use all the time as an alternative to enum values. To demonstrate, let's revisit the enum example I gave previously. In this example, I introduced an enum type to define the three valid string values that could be used for this field: active, inactive, and new. The downside of this approach, as I mentioned in that video, is that defining enums like this actually adds more code to your final output. Often that may be what you want. However, in examples like this, where you want to just restrict certain fields to a limited set of known values, I find type aliases to be far more effective. To rewrite this enum using a type alias, simply change it to this. And now, when you use it, you no longer have to reference the enum type, because using a type alias for this field will allow TypeScript to restrict those values for you. All you have to do is type the string values directly. And there it is, my favorite alternative to enum values. The TypeScript techniques that I've shown in the course up to this point have been pretty foundational, things that you'd use in just about any TypeScript file you'll edit. From this video forward, however, I'm going to be getting into more advanced techniques that you may not use in your everyday TypeScript editing, but ones that will allow you to be far more exact and expressive with your typings to increase the number of issues TypeScript can detect and help you avoid. In this video, I'm going to be showing you how to reference the fields of a given type using the Keyof operator. Using the Keyof operator looks a lot like using the native instance of operator. This line defines a type alias consisting of all of the properties on the contact type. In other words, a variable of this type may only contain values matching the names of the properties on the contact: ID, name, birth date, and status. To show it in action, I can try to create a new variable with this type. And see that the autocomplete options only include the names of the contact properties I just mentioned. This, of course, includes any fields that exist right now, as well as any I might choose to add in the future. So if I add another field to contact, I can see this new field in the list of possible values as well. Note that just like the string union type aliases I showed in the previous video, the contact fields and its values are only available at compile time and not actually compiled into your running code, so they're not available at runtime. Now, this is pretty impressive, but it might not be obvious at first glance just how useful these kinds of types can be. So let me show you a more real-world example, one that I use all the time. This function accepts two parameters, an object and the name of a property on that object. The function then returns the value of that object's property dynamically using JavaScript's object index syntax. This code may be simple, but it's a great example of JavaScript's powerful dynamic typing. Without strong guardrails, however, this dynamic approach can quickly get out of hand and result in easy to create and hard to diagnose bugs. For example, misspelling the name of a field. Without any static typing to help out, JavaScript will happily execute this code and return the undefined value. However, if I introduce a Keyof type to this second parameter, it limits the values of this second parameter to valid property names of the contact type, and TypeScript now correctly highlights my mistake as an invalid value. What's more, as with my example function in the generic types video, the logic in this method has nothing to do with the values of the contact type specifically. So, refactoring it to a generic function makes a whole lot of sense. Just take a second to appreciate just how powerful this is. Not only am I able to pass in any type as the target object to read from in the first parameter, TypeScript readjusts to limit the second parameter, ensuring that it is a property name of the first parameter's type, no matter what that first parameter's type may be. For example, let me now try calling this function again, this time with an object for which I don't even define a type. From this list of properties, I can see that TypeScript was able to inspect the first parameter that I provided and extract its field names, all on the fly. But we're not done yet. Let's take this one step further. Back in the generics video, I showed you not only how to declare a generic type like T in this example, but also to constrain the types that may be used to satisfy that generic type. Well, the Keyof operator is a great way to constrain your generic types. For instance, we can rewrite this function like this. Now, I haven't really changed the way that this works. The second parameter is still limited to the property names that appear on the generic T type, the first generic type. However, what I have done is introduced a second generic type that can be referenced later on in this function. For now, I'll just present this as a cleaner version of this function, but in a few videos, I'll add a few more techniques to this function to make it even more powerful. So keep moving on to the next videos to see what I'm talking about. In this video, I'm going to show you how to take advantage of a JavaScript feature that's been around for a long time. The Typeof operator. If you've never used JavaScript's Typeof operator, it looks like this. If I were to execute the code on lines 1 through 4, I would see in the console the word string and boolean printed out because those are the types of the X and Y variables. Now, this is typical JavaScript behavior. It has nothing to do with TypeScript. In fact, I've been writing JavaScript code like this for years. This is, once again, another example of using JavaScript's dynamic typing system to write very flexible logic. In this case, this function accepts a single parameter named name or contact, the value of which, from what we can tell from the code, it expects to be either a string or a contact object. But here's the problem. We can understand from looking at this code that the parameter should be either a string or a contact value, but TypeScript can't. So let's apply some static typing to this method's signature. Here I've said that this function returns a contact type, and I've used a union type to indicate that it accepts either a string or contact value as a parameter. When I do this, something interesting happens. Because TypeScript now knows that the parameter can only be one of those two types, it can now make much smarter inferences, such as the fact that if the JavaScript Typeof operator returns object, then the parameter must be a contact. Or if it's something other than an object, then the value must be a string value. But that's not all. TypeScript also allows you to use the Typeof operator to define or determine static types dynamically. Consider the following example. First, I define a variable and assign it to a JavaScript object. I don't explicitly set this variable type, but TypeScript is able to infer what it is nonetheless. That's great, but how do I refer to this same type later? Well, like this. With this code, I can make sure that any time someone tries to call this save function, the parameter that they passed must match the same structure as what I've defined on the myType variable on line 36. In all honesty, in most cases, I would probably just elect to simply create an explicit interface or type alias to address this situations. But sometimes using the Typeof operator in this way is a helpful shortcut. However, this approach can be useful in that more dynamic code that you write when you're accepting values of types you don't actually know about until runtime. In this video, I'm going to show you how to determine the type of a certain property or multiple properties of a target object using something called an indexed access type. As its name implies, the syntax for an indexed access type is the same as the JavaScript syntax for accessing a property of an object using the index syntax like this. If I hover over the type, I can see that the type of awesome matches the type of the ID property on the contact type, number. How is this useful? Well, take a look at line 19, where I have a property named contact ID, which references the ID property of the contact type. Well, at least its name references the ID property, but its type just happens to be the same. There's no direct connection between the two. So let's make one. While I haven't really changed the type of the contact ID property here, I have done a much better job of showing my intention that this type should match the type of the ID property on the contact interface. I can do the same thing with these references to contact status. Now let's go back to our original example and explore a little deeper. Deeper into the object structure, that is. Not only can I use this syntax to reference the type of properties, I can actually dig into the properties of those properties. For example, if I change the index to point to the address property of the contact type, which itself is a complex type, I can keep using the same syntax again to drill down into the address type. Like when I choose the postal code property, I can see that the awesome type now matches the postal code type, string. Now, let's turn our attention to the getValue method here on line 36. But first, let me change what this function does just a little bit. Take a look at the handful of contact event interfaces I've defined here. I've also collected all these types into yet another type called contact events, which you can think of as one place to find all of the events having to do with a contact. With that in mind, I'm going to change the getValue method not to read a value from an object, but execute a method. Just bear with me. Okay, I lied. I'm not going to use that getValue method at all, but I lied for a good reason. You see, I know this looks pretty complex, but hopefully it'll be a little easier to digest since you watched me convert the method I already explained. Whether you're mad at me or not, let's go through this. First, I define a generic type T using the Keyof constraint like I showed in the earlier video. Then I use this generic type as the type of the first parameter to the method, event name. In other words, this parameter will accept a string containing the name of any of the properties you can find on the contact events type, deleted, status changed, etc. Then comes the interesting part. The second parameter here is a function which accepts a single parameter, and that parameter matches the type of the property indicated by the first parameter, event name. To really appreciate it and actually make sense of what I just said, you really have to see it in action. Here I've called the method and asked to handle the status changed event name. This is nothing new. You've seen this already. The magic comes in the second parameter. Notice how TypeScript has determined the type of this event parameter is contact status changed event, even though I didn't specify it in this call. That's because I used index access of the contact events type to figure it out on its own. And of course, TypeScript is also smart enough to figure out the types inside the method as well. Here I've handled the status changed event, whose handler expects a contact status changed event. However, the code I've written tries to pass the handler a contact deleted event, which is not correct, so TypeScript yells at me. However, the moment I provide an object that matches the correct contact status changed event interface, TypeScript is happy and those errors go away. Hopefully you can see now that even though it may have seemed like a somewhat trivial syntax, the indexed access typing technique can actually help produce really advanced and powerful type checking. Way back in the beginning of the course, I showed you how to use the any type to make TypeScript revert back to JavaScript's dynamic and unpredictable behavior of dealing with types. It's particularly useful in dealing with situations like this, where you want to extend an object with properties that don't exist on the type that TypeScript originally inferred from the initialization of the variable on line 1. In this case, just add any. And TypeScript is happy to stop yelling at you and let you go back to manipulating the object however you want. The problem is that taking this approach is effectively opting out of type safety altogether. In other words, describing a variable with the any type means it can quite literally be anything, and TypeScript will never get upset. I generally try to avoid using the any keyword whenever possible. In fact, there's a TypeScript configuration setting which allows you to trigger a compile error whenever any is applied. One alternative that you can use to still retain some of the flexibility and dynamicism of the any type is the record type. The record type is a very flexible type definition that allows you to define some structure and even some typing without having to detail every possible property of the type you're trying to describe. The record syntax is very simple. It's a generic syntax with two generic parameters. The first parameter is the possible property values, while the second is the possible property types. For example, I can define a record with string properties and string values like this. Note that my initialization continues to work just fine because the property name name is a valid string and it's assigned to a string value. If I try to assign one of these properties to a numeric value, however, TypeScript tells me that number is not assignable to string. It didn't have a problem with the property name I used. Number is a perfectly valid string value. However, it doesn't like that I'm trying to assign a numeric value to this property, since I've only defined string values in my list of accepted property types. That's fine. I could just use a union to add number to that list. and then that error goes away too. And I can do the same with additional types as well. For example, I can add a Boolean valued property and a function valued one too. And then add those types to the list of accepted types and watch the errors go away. Notice that other errors, like when I try to assign the x variable to some completely different type, are still very much there and still very legitimate warnings. I don't want to be able to assign x to some other type of value. Now that we've made the property types dynamic, let's take a look at the property names themselves. Say I have this function that accepts an array of contact objects and a query object on which each property on the query object matches the name of a property on the contact type and contains metadata to filter the contacts by. This function iterates through the properties of each contact and compares them to a filter defined on the property with a matching name on the query object, if there is one. For instance, the contact's name property is compared with the name property on the query object. An example call to this method is shown below, right here. Now, how can record help in this scenario? First, I'll use the record syntax that I already showed in order to define an object who can have properties of any name, but all of those properties' values must be a query object. Honestly, this is really great, and we could probably stop right here. But let's make it specific to the properties on contact. But let's limit the properties of the query object to the properties on the contact object by using our old friend, the Keyof operator. And I can see as soon as I do this, TypeScript warns me that phone number is not a valid property on contact. So I'll remove it. And now TypeScript yells at me with this not so straightforward error that I haven't provided a value for every property of the contact type. I'll get back to that later. The next thing I need to do is cast the call to object keys to the same type because for some reason, TypeScript is not yet smart enough to infer that. Once I do that, I can see that TypeScript can now infer that the type of the property query object is query, which means that matches must be a function. From these examples, I hope that I've proven just how simple and useful the record type can be in replacing the majority of places where you might otherwise give up and use the any type instead. And don't worry, I'll show you how to fix this error in another video. In a previous video, I left you hanging with a TypeScript error that was caused by using the record type to define a query object whose properties were limited to the properties of the same name on the contact type. Now, that worked great to find the property that I previously had defined, which didn't match any of the properties on the contact type. Once I removed that property, however, I faced a new problem. TypeScript is now yelling at me that I haven't provided values for all of the properties of the contact type. The real problem here, though, is I don't think that this is a problem. I want to choose only a subset of those contact type properties in this query object. In this video, I'll show you a few utility types that allow you to extend from existing types like record, but pick and choose which properties you want to include and exclude in your new type. First up, let's solve this current problem using the partial helper type. The partial helper type is a generic type, so I'll use it to wrap my existing record-based type using this syntax. Notice how the error at the bottom immediately went away when I applied the partial type. This is because the partial helper type creates a new type that looks exactly like the type it wraps, but with all of its properties defined as optional. This means that you can define as many or as few of them as you wish. In other words, now if I want to query only the ID and name properties and no other properties, like I'm doing on lines 49 and 50, I can only define query objects for those specific properties. What if I want to do the opposite, however, and restrict the usage of certain properties? For example, what if I don't ever want to allow queries on the address property of the contact class? Well, there's another helper for that, and it's called omit. Like partial, the omit helper is a generic type that wraps another type and copies that type's definition. But, like its name suggests, it allows you to omit certain properties from that cloned definition. Unlike partial, however, the omit helper requires a second generic parameter, the list of property names that you'd like to omit. For example, in order to omit the address property from this definition, I'd simply add it as the second generic parameter. And now I can see that it's no longer in the list of available properties. Of course, I can list as many properties as I like using a union type. With this definition in place, I can see that my contact query type now has only two possible properties, ID and name, and neither the address nor the status properties are available. And both of the remaining properties are optional due to the whole thing being wrapped in the partial helper. In this example, omit is being used to exclude certain properties, leaving me with only a few. This means as new properties are added to the wrapped type, the contact type in this example, those new properties also become part of this new type. If that's not what I wanted, if I wanted to limit this type to only the ID and name properties, no matter what other properties get added to the contact type, I can use yet another helper named pick. As its name implies, pick is the opposite of omit. It creates a new type using only the properties named by its second generic parameter. In this example, I've limited the allowable fields to only ID and name, no matter what new fields may get added to the contact type in the future. And finally, one last useful utility type is the required type, which is the opposite of the partial helper, turning all properties of a type to required properties instead of optional. Here I've used the require type to wrap the contact query type that I've been demonstrating and see that it has inherited the same properties as the contact query type, only those properties are now all required instead of optional. I use these utility types all the time, especially the partial type, to quickly make new types based on existing ones, but modifying them slightly in order to make their properties optional or remove those properties altogether. I expect these types will make plenty of appearances in your TypeScript code as well. In the previous video, I introduced you to the record utility type, which allows you to construct a new type by referencing the fields of another type. Defining new types like this is an incredibly useful technique, and using the record type to define them is a quick and easy way to create simple references like the one I've created here. However, more often than not, the new type you're looking to create is more complex than what's shown here, and in those cases, I like to use a different syntax called a mapped type. In its basic form, a mapped type definition looks like this. This mapped type definition uses a property indexer syntax, the open and close brackets, in conjunction with the key of syntax I used in the record-based example in order to enumerate all of the keys of the contact type. In other words, this example completely duplicates the previous type alias that used the record syntax, complete with the question mark at the end to make all of the mapped properties optional. The reason I like the mapped type syntax better, however, is that while it does make the simple definitions like this one look a little more complex, it actually allows you to make more complex definitions much more readable. For instance, one of my all-time favorite uses of this approach is to use the name of the key that I'm referencing to make one boilerplate line of code that adapts to each target property. Let me show you what I mean. Let's revisit this query type that I created a while back, specifically the type of parameter that gets passed into the matches method on line 19. Without an explicit type, TypeScript infers this parameter to be the any type. But remember, we want to avoid any wherever possible. So let's convert this to a generic type. And use that new generic type as the parameter type for the matches method. Once that's complete, I can go back to my map type to take advantage of this new generic parameter and pass the type of the mapped property like this. In order to explain what I just did, let me show you the resulting type. A mapped type where not only have all of the property names of the source type, contact in this case, been copied over, but I've been able to reference the types of those properties as well. I did that using the same property indexer syntax that I would use to access a value of an instance on the contact type, the open and close brackets. Why is all of this useful? Well, now I've got full static typing in my query objects. For example, when I provide a query function for the ID property, the query function's generic type parameter is number, the same type as the contact ID's property. Likewise, the parameter type of the query object for the name property is a string, the same as the contact's name property that it was originally mapped from. You may have noticed that TypeScript is now complaining that it can't adequately predict the type of value that will be retrieved when we iterate through these properties on line 34. I can fix that issue by telling it that it will be some kind of type from one of the properties on contact, but it doesn't need to care about which one. Now that it's all working, you might be thinking that this approach seems a little complicated or advanced, or maybe a little overkill. However, I find using map types in this way to be one of the most useful techniques to fill those static typing gaps where I might otherwise find myself defaulting back to the any type. I expect you'll be surprised at how often this will come in useful to you as well. Now, I've shown you a lot of content since our last challenge, but I've waited before I showed you this next challenge because it will take almost everything I've shown you since then in order to complete this one. And here's your challenge. Replace this any type with the right type for this scenario. That's it. Now, what's the right type? Well, it's this object right here. An object that allows for properties that match the properties of the objects in the array above it. And each of these properties on this query object should be a function that accepts the value of that property and returns true if the value matches the function and false if it does not. You'll know you've got it right when you can hover over this and see the type string instead of this TypeScript warning. Seem familiar? Well, yeah, it's basically the same example code I've been showing you for the past 6 videos. But just because I've already shown you how to do it doesn't mean it's easy. Even though it's only going to end up being one line of code, and despite the fact that I've already shown you exactly how to do it, it's still probably going to take you a while to figure it out from scratch. So I'd give myself at least 10 minutes for this one. And try your best to do it without cheating and going back into previous videos to see what I did. For this challenge, I asked you to implement the same scenario that I've been showing you for the past 2 chapters, and to try to do it without going back to see what I've done in those videos. Now, I'm going to show you two ways to solve this problem. The first solution is simpler and easier to implement, but it doesn't actually solve the problem in its entirety. Regardless, it's worth showing, so I'll start with it. That solution I'm talking about is to use a record type like this. This gives me the ability to create a record object whose property names match those of the target object. Then I can define the type for the query function, the thing that checks the value of the property, like this. And that's the end of that solution. Sure, it works, but it only gets me part of the way there. This still says that the type of this name property can either be a string or a number, but that's just not true. I know it's only a string. So let's take another pass. This time, instead of using a record object, I use an indexed accessor type like this. First, I define the name of the property. I'll use Keyof to limit it to only property names that exist on the type T. Then I'll give this property name a generic type name and use that as the type of the parameter in the query function for this field. And finally, since I don't want this object to require a query for every property of the target object, I'll make the property optional like this. And that's it. I've got my fully typed query object. Now, the reason this works better than the record solution is simply because with this approach, I'm defining each individual property rather than the whole object at once. So the value of tprop will be the name of the property on the left side, and I can use that same property name to figure out the type of that property on the right side. Now, if you had trouble with this solution, don't be concerned. These concepts are pretty hard to get the first time around. Try reviewing the past two chapters to really understand what is going on in this solution, and then come back and try it again. It may seem like a lot of effort to learn this, but trust me when I say it's worth it. These are the kinds of types that will really bring your static type checking to the next level and catch many more of those hard-to-find bugs before they get shipped into production. In this chapter, I'm going to show how to use an incredibly powerful TypeScript feature named decorators. The easiest way to understand decorators is to think of them as metadata that you can add to your classes, methods, and even getter and setter properties. In fact, you can add far more than just information. You can actually extend these elements with additional behavior, allowing you to add that behavior to your code without actually changing your code. The typical example of decorators in action is a logging decorator. Let me show you. This example class has logging statements at the beginning and end of each function. This helps diagnose problems more quickly because you can determine which functions have run and whether or not they completed. It also features a mechanism that protects the method from being called by users who don't have proper access. Though this is the behavior that we want, there are a few things that are less than ideal about this code the way that it's written now. First off, this is a decent amount of duplicated code. Next, it's tedious to write, not to mention error-prone, considering the fact that developers are required to type the method name freehand. And finally, this logging and auditing code is an auxiliary function. It doesn't actually have anything to do with the actual purpose and function of these methods, which is to save and retrieve contacts in this case. In other words, it's just noise. This scenario, however, is a perfect opportunity to apply decorators to both centralize and simplify this code. For example, what if we could just write this and then eliminate the logging statements? And this, and eliminate the access control statements. Doesn't this code look so much cleaner and easier to read? Plus, it has the added benefit of being able to easily change how and where those log and audit entries are stored. Plus, it has the added benefit of being able to easily change how and where those log entries are stored, or how we apply our authorization logic. These are exactly the kinds of scenarios where decorators shine. And in this chapter, I'll show you how to create these decorators. Before I continue, however, I must warn you that decorators are actually a proposed addition to the JavaScript language itself. And as this proposal evolves, its final implementation may actually begin to differ from TypeScript's implementation. If you're worried about writing code that may conflict with a future JavaScript standard, then you may want to simply view this chapter to learn what decorators can do, but wait to implement the techniques in your own code until the standard has been finalized. If, however, you trust that TypeScript will support you in writing code that will at least compile to JavaScript compatible code, then by all means, please continue on. I certainly use decorators in my code. In order to really make this point clear, TypeScript actually encourages developers to opt in to decorator support via a configuration setting. So be sure to do that right now. Simply open up your tsconfig file and set the experimental decorator settings to true. There's also one more thing, which is not technically required to use decorators, but it's a really valuable tool, and that is runtime metadata. I'll explain exactly what this is in later videos, but while we're here, let's go ahead and add support for it so it will be available to us later. To enable it, you'll first need to set another setting, emit decorator metadata, to true. And then you'll need to install the reflect-metadata library like so. This library implements polyfills for another set of proposed ECMAScript features, which are considered experimental now, but should hopefully be approved and implemented around the same time that decorators become widely available. And now, with all this code in place, continue on to the next video where I'll show you how to create your first decorator. The best way to learn how to create a decorator, in my opinion, is with a method decorator, as I find it the most straightforward to understand and implement. As its name implies, a method decorator is a decorator that you apply to a method. On lines 19 and 29. Implementing a method decorator is as simple as writing a function that looks like this. This function gets executed at runtime and accepts 3 parameters. The first parameter, target, is the object that the decorator is being applied to. In the case of a method decorator, it is the instance of the object that the method belongs to. The second parameter, property, is the name of the property that the decorator is applied to. And finally, the third parameter, descriptor, is an object containing the current metadata about the property. Now, this descriptor object is actually the same for any property of any object, regular fields, getters, setters, and methods. In the case of a method, however, this value property will be the one we're most interested in because its value is the function that is executed when the method is called. When creating a method decorator, you have 2 options to modify the behavior of the method. The first option is to simply edit the descriptor in place like this. This approach leaves the existing descriptor in place and just modifies its properties. The second option is to return a brand new descriptor object like this. Once returned, TypeScript will replace the method's current descriptor with this new one. Now, neither approach is inherently better than the other. It's mostly just a matter of style and the current problem you're trying to solve. Now, let's get back to our example implementing this authorized decorator, which throws an exception when the user is not authorized to access a method. To do this, I'm going to replace the descriptor's value property with a new function. And I'll start this function by checking to see if the user is authenticated, and if not, we'll throw an error. This is the new logic that we want to add to the method, but keep in mind that this new function completely overwrites the current method, so we still need to execute the original logic. To do this, I'll make a copy of the current method before I overwrite it. And then I'll simply call that function from within my new function using the apply approach. And that's it. We've wrapped the method's logic with our own. Here is where you can really let your imagination run wild with what you can do in this code. For example, you can wrap every method call in a try-catch block and automatically log every exception that occurs, but still not affect the way the application behaves. Now that the decorator is ready, we can apply it to whatever methods we like using the syntax I showed in the previous video. With this in place, our decorator now guarantees that users are authenticated in order to access these methods. Otherwise, an error is thrown. However, you may notice that this is not actually a drop-in replacement for the code that I had here before. This code checks not only that the user is just authenticated, but that they actually belong to a particular role. In order to implement this behavior, we're going to need to add a parameter to our decorator so that we can pass in the role that should be checked. Head on to the next video where I'll show you how to do exactly that. In the previous video, I showed you how to create a method decorator to wrap a method's functionality, and I used this authorized decorator to demonstrate. I also pointed out, however, that this implementation didn't allow us to pass in any parameters, such as which role we expect the user to have, like the existing code does. The problem is that a decorator must have the signature that my example decorator currently has with the target, property, and descriptor parameters. How then do we pass in a custom parameter like I want to do here? By wrapping the decorator definition in another function called a decorator factory. As its name implies, a decorator factory is a function that creates decorators. In other words, our current decorator definition now becomes the return value of another function, like this. With this wrapper in place, we are now free to define whatever signature we like, including whichever custom parameters we want. For example, I can now add the name of the user role that I want to ensure the user belongs to. The decorator function within this factory can then access these parameters in its logic like this. With this decorator and factory in place, that code that I showed in the beginning will now work just fine, accepting the role that I'd like to check for, or allowing me to add any other custom parameters in logic I might want to add in the future. Now that I've shown the fundamentals of how decorators and decorator factories work with methods, I'll show you how to apply decorators to classes. At a high level, the approach is pretty much the same. For example, if I wanted to create a decorator to freeze a class to prevent any changes, I can create a function that accepts a single parameter with the function type like this. and we apply the decorator to the class by placing it just before the class definition, like this. So far, so good. It is the same familiar syntax that is used to create method decorators. The biggest difference, however, is what is actually being decorated. In other words, what exactly is the target that this parameter references? As the function type implies, the target being passed to the class decorator is not the object being created when the class is instantiated. Instead, it's the class's constructor function. In other words, you can think of it more like this. With that in mind, let's actually change the name of the parameter, just to be really clear what it is. I can now implement this decorator by calling the object.freeze method to freeze the constructor so that it cannot be modified after it's defined. We'll also want to freeze its prototype as well. And that's it. We've now created a class decorator to modify the class's constructor function. To be honest, however, I've never had the need to modify a constructor function with a class decorator. Most of the time, I use class decorators to dynamically add properties or behaviors to a class at runtime. To do that, we take a slightly different approach in our class decorator, and instead of modifying the constructor function as it's passed in, we actually return a brand new class. It looks like this. Let me create a new decorator named Singleton. And for the type of the constructor parameter, I'm going to use any for right now. I'll come back to that later. Then I'm going to simply use the standard class syntax to define a brand new class that derives from the one that was passed in. And then I'll simply return that new class. And that's it. I've now dynamically redefined the decorated class by creating and returning a whole new class behind the scenes. While this new class is technically not exactly the same as the one that was passed in, it does extend the class that was passed in, so it still retains all of the original class's members and behaviors. Once this code is in place, I can do whatever I want, such as create a static property. Or add behavior to the constructor, such as checking to make sure that only one instance of this class has been instantiated. To do this, I'll add the basic constructor, which calls the base classes constructor via the super method. But because this decorator can be applied to any class, and we don't know what, if any, parameters that target constructor might have, so we'll use the spread operator to accept any and all parameters being passed into the original constructor and pass them right on to the base constructor. With this in place, I can finally add my custom logic. First, I'll check to see whether another instance of this class has been created. If another instance has been created, I'll throw an exception. Otherwise, I'll save a reference to the newly constructed instance at the end of the constructor so that I'll be able to check for it next time. And that's it, a fully implemented example of a class decorator. Before we end this video though, let's go back and fix the constructor parameter type, if only because I try to avoid the any type whenever possible. The reason I originally converted this to the any type was because the function type just wasn't going to work. TypeScript won't let you create a new class that derives from a regular function. Instead, we need to use a generic type definition that describes the special behavior of a constructor function, which looks like this. I won't get into the detailed explanation of this generic type, except to scroll down to where we've used our singleton class decorator and see that the absence of compilation errors shows that it's exactly the type that TypeScript was looking for. So far in this chapter, I've shown you how to create method decorators and class decorators. In this video, I'm going to show you about the third kind of decorator, the property decorator. As its name implies, property decorators are decorators that are applied to properties of a class, like the context property of our contact repository example. And you apply a decorator to a property the same way you apply one to a class or a method, like this. Here, I'm applying a decorator called auditable, which I'll create in a minute, to the contacts property. The implementation of this decorator will log a message to the console anytime the value of this property is changed. Since methods are just properties of a class that happen to be functions, the definition of a property decorator looks very much like a method decorator, a function that accepts two parameters, the target and the property name. And, just like the method decorator, these two parameters correspond to the instance of the target object that is being decorated and the name of the property being decorated. Now that I've defined the decorator function, let's implement it. To do so, I'm going to use the object.defineProperty API to easily define getter and setter functionality on this property. The short explanation of this code is that first I save the initial value of the property on line 55, then overwrite the property with a custom getter and setter using the object.defineProperty starting on line 58. In the custom setter on line 60, I log a message to the console on line 61 anytime the property value is changed. Unfortunately, a more in-depth explanation of the Define Property API and its pros and cons is outside of the scope of this course, which is, quite frankly, why I saved this video for last. Most of the property decorators I make end up looking almost exactly like this. However, I highly encourage you to get a solid understanding of JavaScript properties and the Define Property API before trying to do anything too advanced in a property decorator. Despite this warning, however, I do still encourage you to use property decorators to make your properties far more dynamic than just saving and retrieving their values. At this point in the course, I've shown you all of the TypeScript syntax that you'll need to know in order to use TypeScript successfully in your day-to-day development. In this chapter, I'm going to shift the focus to using the syntax you've already learned, but in a different way. And in fact, I'm going to start by going back to a JavaScript feature, modules. Put simply, JavaScript modules enable you to link code that is distributed across many files. Let me demonstrate. Here is an old-school JavaScript web application stored in several files. And in our web page, we use HTML script tags to download and load each of these files into the browser's memory. As we do, the contents of each file get loaded into the same shared memory space. That means that when I define a function in one file, and then define another function in another file with the same name, and then load both of these files like I'm doing here, the last function to be defined overwrites any others defined before it. With modules, however, each file shares its own memory space, so any function or variables that are defined within that module stay within that memory space and do not leak out, avoiding these kinds of collisions altogether. What's more, Modules can load from other modules. And since just about all modern browsers understand modules, they're even able to download these other modules on the fly based only on these kinds of references. This means that we no longer have to worry about loading every file of our application up front, but instead let the browser load them for us as they're needed. Now that I've shown modules in action, check out the next video where I take a few steps back and show you how to write module-based code from scratch and how TypeScript can help you do it. In the previous video, I very quickly showed you an application that did not use modules, and then that same application after it had been converted to use modules. In this video, I'll back up to that pre-modules application and walk you through exactly how to convert it to a module-based application. This is the entry point of the application, app.js. The code in app.js relies on a utility function formatDate defined in the util.js file. And it gains access to that function simply by the fact that we happen to be loading both of these files into the same browser window. The moment we convert these files to TypeScript, however, TypeScript complains about the fact that it doesn't know about function formatDate. To make TypeScript happy again, we'll need to tell it where it can find this function. That is, we'll have to explicitly import this function from the other file. However, before something can be imported by a module, it must first be exported. So let's do that. In order to make a function or variable defined in a module available to other modules, we simply export it. That is, we add the export keyword just before its definition, like this. Then we can jump back to app.ts, the module that wants to use this function, and import the function using this syntax. I start with the import keyword, and then I say which module I want to import from. Since this is a local file, I'll just provide the path to the file without the extension. This adds the reference to the target module. Now I need to declare what exports I want to import by listing them inside braces, like I'm defining a JSON object. And that's it. I can now use this function as if it were defined locally. And that is your quick intro into modules and how to use them with TypeScript. But be aware that there's plenty more you can learn. However, it's outside of the scope of this course since it's all just JavaScript and really just doesn't have much to do with TypeScript. I highly recommend that you search our outstanding video library for JavaScript modules to find many great videos to help you use modules to their fullest potential. In the imports and exports video, I showed you how to convert an existing application that relied on global functions to modules using imports and exports. However, if you have a large existing code base that relies on global imports for existing JavaScript files that can't be converted, don't lose hope. In this video, I'll show you how to document that JavaScript code so you can continue to use those dependencies without a problem. To begin, I'll go back to the same application that I just converted, back to before I converted it. Remember, this was the version of the application that was explicitly loading all of the JavaScript files. I'll start out by converting the app.js file to TypeScript, just like last time. And I'll see that error again. TypeScript doesn't know about a function named formatDate, just like last time. However, in order to fix this problem this time, I'm going to create my own version of the TypeScript declaration files I showed you way back in the first chapter. As you might recall, these files have a d.ts extension. Since TypeScript is going to read the contents of this file no matter what name I give it prior to the d.ts extension, I'll just call it globals.d.ts. Then I can create whatever type definitions I want in this file. In order to tell TypeScript that what I'm about to describe will be in the global namespace, I'll write the following. This tells TypeScript that everything I write inside these braces should be available in the global namespace. Notice the error here. This is TypeScript telling me that I can't use this syntax just anywhere. It has to be inside of a module. That means I need to export something in order for TypeScript to treat this as a module. So I'll just define an empty set of exports. With that out of the way, I can now define whatever global definitions I like. For example, my function. Notice how I'm just writing the definition of the function and not the implementation of itself. And of course, this is TypeScript after all, so I can give it a parameter type and a return type. And while I'm at it, I can add some documentation too. Once I'm all done with the definition, I can switch back to the TypeScript code that uses it and see that not only has TypeScript found my definition just fine, but I even get the full documentation in IntelliSense as well. That's all I need to do in order to address this particular example, but rest assured that you can use any of the TypeScript concepts that I have shown in this course inside of these declaration files to describe any situation you may come across in your custom code. It's also important to note that writing type declarations like this doesn't actually ensure that the code is available at runtime. For example, if I were to forget to include the script tag that loads the util.js file into my browser, my TypeScript code would continue to compile without any errors, only to crash at runtime when it goes to execute a function that doesn't exist. Regardless of that caveat, having this ability to define types for JavaScript code that lives outside of your TypeScript files is a great way to get full TypeScript support when integrating with existing JavaScript codebases. In the previous video, I showed you how to document code that TypeScript isn't aware of. In this video, I'm going to show you how to extend the definition of a type that TypeScript is aware of. What do I mean? Well, let's say that you have this class, and you use some good old-fashioned dynamic JavaScript to add some behavior to it after an instance of it has been defined. Well, TypeScript doesn't like that you didn't tell it about that save property when you created the original class definition. Now, you could just go back to the definition and define the function with an empty implementation, but what if you don't want to do that? Or what if that class definition is a third-party library and not your code? In order to extend a class definition, whether you own the class definition or not, you can simply define an interface with the same name as the class, like this. Then fill this interface with whatever you would like that class to expose. And notice that the error goes away and it's replaced with full type information. This is a TypeScript feature called declaration merging, which means that TypeScript is perfectly happy to allow you to extend an existing interface with a new one. Unlike JavaScript code, creating another interface with the same name as an existing interface merges the new interface into the existing one, rather than overwriting or replacing it. And yes, I did say extend an existing interface, even though the example I'm showing here extends a class definition. That's because TypeScript considers every class definition to also be an interface. It's just an interface that happens to have an implementation. To be honest, I don't use this type of declaration merging too much, usually only when I'm adding behavior to a third-party library. However, the one scenario where I do use it quite a bit is to strongly type my global variables in a web application. You know, the ones that look like this. Notice that if I hover over the window variable, I'll see that the built-in TypeScript types include an interface definition for the browser's window object. one that I can extend. I'll just create another globals.d.ts file like I did in the previous video and add my global declaration here, just like I did in the last video. Then I'll define an interface with the same name as the existing interface window. And once I have that, I can put anything I want in there, just like I did with my global function. With that in place, I can switch back to my application and see that the error has been replaced with full type information. Note that you can use this trick to extend any class or interface that you reference in your application, regardless of whether it's your code or a third-party library, and you should feel free to do so. If you're learning TypeScript, you're probably looking to run your code in either the browser or Node.js. Unfortunately, the code I've been showing won't actually run in either of those environments as it is, but in this video, I'll show you how to fix that. I'll start with Node.js, since that's the easiest. As of this recording, Node.js expects module imports to use a different syntax than the one I've been showing here, which means that if I try to build and run this application, I see this error. Even though it's not obvious, this is Node's way of telling me that it doesn't support this import syntax in .js files. However, having TypeScript output the code that can run in Node is as simple as tweaking a TypeScript config setting. Simply set the module configuration setting to common.js, the type of module system that Node uses. Now, when I save this, run the TypeScript compiler again, and check out the output code, I can see that it uses the require import syntax to make the module imports, which is the way that Node.js expects imports to be declared. And I'll run the app again real quick, just to prove that it does work this time. So that's compiling modules for Node applications. Sadly, compiling for web applications is not so straightforward. While it is true that modern web browsers do have the capability to understand and load module-based code, it's not something I ever use in practice. For module code that runs in the browser, I highly recommend that you use a separate bundling and minification tool, such as the wildly popular Webpack or the low configuration parcel tool. In addition to understanding modules, these tools will also help optimize your code